All right, last lesson for circular motion, work, and energy is the conservation of energy. So we've used this in Science 10, and we're just going to bring it back and kind of increase our use of it. So the law of conservation of energy states that the total amount of energy in a system remains constant, that energy may only be transformed from one type to another. So we can go from kinetic to potential or kinetic to heat, but the amount of energy is conserved. So for example, a skier starting from rest at the top of the hill at COP has gravitational potential energy due to the vertical distance from the top of the hill to the bottom. As she slides down the hill, her gravitational potential energy becomes less and less because she's reducing her total vertical distance. And while her kinetic energy, aka her speed, becomes larger and larger. If the hill was frictionless, all of her gravitational potential energy from the top of the hill would be transformed into her kinetic energy at the bottom. Of course, there's a substantial amount of friction between the skis and the snow. Therefore, some of the gravitational potential energy will be converted into heat energy and some will be converted into kinetic energy. So in Science 10, what we would have done is we would have said EK at the bottom of the hill is equal to the potential energy at the top of the hill. Now that we've dealt with friction, we're going to also start including this heat energy as well. So the potential energy at the bottom of the hill is what she had at the top of the hill, subtracting the heat energy. What this is, the conservation of energy problem solving, is just how to set up our problems. So we are going to determine the different forms of energy that are present at the beginning of the problem. So list out what you know they start with in terms of energy. Okay, so if the object is higher than it was at the end of the problem, it has potential. If it has motion, it has kinetic potential. If it's a spring or an elastic that's being stretched, it has spring potential energy or elastic potential energy. And if a force is being applied over a distance, then work is being done. So don't forget that we can include work in this. Then we're going to determine the forms of energy that are present at the end of the problem. List them out. Okay, again, using those kinds of ideas. And then we're going to apply the principle of conservation energy, saying that our initial is equal to final. We'll write a mathematical equation that says that. We're going to substitute in and get going. So you are creating a new mathematical equation for each situation that you encounter. So do not try to memorize how each of these are set up. They're changed by each different scenario. Understand those first 4 steps of how to, and you'll be able to solve any of these problems. Okay, so first example, a 50 kilogram object falls 490.5 meters. What is the speed of the object just before impact with the ground? So what did we have initially for energy? Initial. Well, initially, they were starting at a particular height. If they have height above where they end, they have gravitational potential energy. Again, there's 2 different types of potential energy, There's gravitational and elastic. At the end, so the energy in the final, at the end, the object will have fallen, so it no longer has gravitational potential energy. It only has kinetic energy. There's no other types of energy being discussed here. They haven't talked about friction, air resistance, anything. So we can always start with the idea that the final energy is equal to how much energy we started with. So the final energy is equal to initial energy. In this case, we decided that the final energy was kinetic energy. So EK is equal to EP, and this was gravitational. So 1/2 mv squared is the formula for EK. And the formula for EP for the gravitational is mgh. So we've equated these two. We can sub in what we know. Something to note, because I could technically divide this side by m and I could divide this side by m, I don't actually need mass in this equation. I could be left with 1/2 v squared is equal to gh. Since we're looking for speed, I'm going to solve this equation for v. So v is equal to the square root of 2 times gh. Subbing in what we know, remember this can be a positive or a negative. So 2, and in this case for g, we're using 9.81 meters per second squared. We do not use the negative, only the positive version of g. So kind of like an absolute value, if you will. The height it fell, 490.5 meters. And we get positive or negative 98.1 meters per second. Now, because we're being asked just for speed, we don't need to include a direction. However, I do know that it's traveling downwards. So you could say 98.1 meters per second down. But again, speed is a scalar quantity, so we can just say 98.1 meters per second. So if you note in your EK, EP formulas, none of them are vector quantities. So we don't need to include the positives or negatives. That's how we get away with using the positive of g. So you do not need to consider this. I've just shown it because we know what's happening here, but it's not going to be marked as a vector value. Okay, a snowmobile driver with a mass of 100 kilograms is traveling at 15 meters per second and they slam into a snowdrift. If the driver sinks 0.5 meters into the snowdrift before stopping, what is the retarding force applied by the snowdrift? So the force that is slowing them down here. We're looking for a force in the end. Now, you need to remember that work is equal to the change in energy. So our initial energy is all kinetic. They're moving at a speed. They do not have height. So it's kinetic energy. The final energy, all of their energy is converted into work. Work is done on the snowdrift. Again, because work is equal to energy. So the initial energy is equal to the final energy. The initial energy was kinetic, so EK. And the final energy in this case is work. Okay, so EK is 1/2 mv squared, and work is force times the distance applied. Now this is the distance that the snowmobile goes into the drift. We're looking for force here. So F is equal to 1/2 mv squared over the distance applied. So 1/2, 100 kilograms, 15 meters per second, all squared, all over 0.50 meters. And this force is 22500 newtons. Remember, that's the unit of force, which, because we have two significant digits from the distance, is 2.3 times 10 to the 4 newtons. I'm not sure where this 5 came from. It appeared in our notes and the previous notes. I just usually copy and paste the answer up there. So there was a difference in the order of magnitude. Let me know if I'm wrong, but I did this a couple times just to double check. All right. A 5 kilogram object is thrown vertically from the top of a 50 meter tower with a speed of 15 meters per second. What is the speed of the object at the bottom of the tower just before it hits the ground? So the initial energy is kinetic because they are throwing it, and potential energy. So we have two types here. The final energy is kinetic energy only at the bottom of its height. So initial energy is equal to final energy. Initial energy is EK and EP. And our final energy is EK. And I'm just going to say EKF and EKI, again, because it's going to appear twice. All right, EK is 1/2 mv initial squared plus mgh. And that will equal 1/2 mv final squared. Again, these are speeds, not vector velocities, so we don't have to put in positives and negatives. Lucky us. All right, once again here, mass is in each term, so I can divide both sides by m. Again, if I have this addition statement on top of my fraction and I'm trying to divide m out, m must be in each term, and it is. So we can cancel m's, and I'm just going to be left with 1/2 vi squared plus gh equals 1/2 vf squared. If you rearrange to solve for vf, vf is equal to the square root of 2 times 1/2 vi squared plus gh. Make sure that you are comfortable rearranging your formulas. This can also be written as vi squared, because our 2 cancels here, plus 2gh. Either or. All right. V initial, the initial velocity downwards was 15 meters per second, that's squared, plus 2 times 9.81 meters per second squared, times the height, which was 50 meters. Notice again that mass doesn't come into this. You can include mass. You don't have to cancel it like we did here, but it does just help simplify. I get 35 meters per second. All right. A bullet, a 5-gram bullet, enters a wooden block at 350 meters per second and exits the 20 centimeter wide block at 150 meters per second. What was the force applied to the bullet by the block? Initially, at the very start of this problem, the energy that it had was just kinetic energy. Okay. So I drew myself a little diagram here to see the energy transformation. So initially it had EK. Then it hit the block and it has to do work to go through the block. Then it exits with kinetic energy final. So as it's starting its journey, it only had potential energy. Therefore, these two pieces are the final energy. So that kinetic energy was transferred into work done on the block, as well as kinetic energy. So energy initial is equal to energy final. The initial energy is EK, and the final energy is work done on the block plus EK final. All right, kinetic energy is 1/2 mvi squared, because we're going to have two different velocities, which is equal to the force done on the block plus 1/2 mvf squared. All right, masses cannot cancel because mass does not appear in every term. In this case, we are reorganizing to find force. Force will be equal to 1/2 mvi squared minus 1/2 mvf squared, and that will be divided by the distance through the block. Okay, so this was the distance and the force on the block. All right, I'm just gonna give myself some more room here. 1/2, the mass is 5 grams. Now we have to change that into kilograms, so divide by 1,000 times the initial velocity, 350 meters per second, which is squared. Take away 0.0050 kilograms times the final velocity squared. So 150 meters per second squared, all divided by the distance through the block. The block was 20 centimeters wide, so that is 0.20 meters. All right, I solved this piece by piece, so 306.25 Newton meters was our first term. Take away 56.25 Newton meters, also known as a joule, but I'm going to end with newtons, so I wrote it as that. Remember, a Newton meter is equal to a joule. Still dividing by 0.20 meters, just to simplify my work there, 1250 meters. We had two significant digits from our 20 centimeters and our 5-gram bullet, so we should really write this as 1.3 times 10 to the 3. Sorry, not meters, that should have been newtons. Last page. A 25 kilogram object resting on the top of a 15-meter high inclined plane begins to slide down the plane. At the bottom of the plane, the object has a speed of 14 meters per second. So regardless of how this has traveled, our plane was 15 meters high. So it has potential energy to begin with again. So initial energy was potential only. And the final energy, what did that convert into? Well, it converted into kinetic, but it also turned into heat energy. Because of friction holding it back, the object would get warm. And that is a source of energy as well. We just don't have any other calculation for it. So how much energy was produced? Well, we always go back to EI is equal to EF. So the initial energy was potential energy, and the final energy was kinetic and heat. So potential energy is mgh, which equals 1/2 mv squared. And we don't know anything about EH, so we're just going to leave it like this. It's also what we're solving for. So I'm just going to input everything and then rearrange and solve. So 25.0 kilograms times 9.81 meters per second squared times the height of the object is equal to 1/2 the mass times the velocity at the bottom squared plus EH. And I got that EH is equal to 1228.75 joules, which I should round to 3 significant digits, so 1.23 times 10 to the 4 joules. If this incline is 35 meters long, what is the frictional force? So we know the energy lost to heat along those 35 meters. Remember that work is equal to the change in energy. So force times distance is equal to the energy here from friction or heat, whatever you'd like to call it there. All right, well, we're looking for the force of friction. And the distance it covered was 35 meters. And so the force of friction is equal to 35.1 newtons. All right, last one. A toy car with mass of 348 grams is pushed up against a compression spring. The spring is compressed by 5.3 centimeters. When the car is released, its final speed is 7.3 meters per second. What is the spring constant for the compression spring? So we've taken a spring against maybe a wall here, and we've put a car up against it or toy car and pushed it in a little bit. So the total amount compressed, so the change from here to where the car started, was 5.3 centimeters is what that's saying. Okay, so our initial energy was potential energy. And this time it's not gravitational, it's elastic or spring energy. The final energy is going to be kinetic energy of the car. So EI equals EF, therefore, our elastic potential is equal to EK. Elastic potential energy is on your formula sheet by underneath potential energy, the gravitational form. So this is 1/2 kx squared, where k is the spring constant and x is how far that is compressed. And this equals 1/2 mv squared. So solving for k, our halves cancel because I can multiply both sides by 2 and cancel that out. So k is equal to mv squared over x squared. So 0.348 kilograms, don't forget to turn to kilograms, times its final velocity is 7.3 meters per second. And that's got to be squared all over how far the spring was compressed in meters. So 0.053 meters. That is 5.3 centimeters in meters. I got that k is equal to 6602, and this unit is Newton per meter. And so our final answer with significant digits, 2 significant digits, should be 6.6 times 10 to the 3 newtons per meter.